Okay, so in this section, we are going to now start talking about the two main types of compounds that we're going to encounter in our class, which are ionic compounds. And we're also going to be looking at another category called covalent compounds, which are sometimes referred to as molecular compounds because these types of compounds exist as molecules. So just a quick refresher on the term compound. Okay, now remember, compound is a type of pure substance. Okay, and a compound, being a type of pure substance, has a constant composition. And what this means for these compounds is that they're made up of, or they're composed of multiple elements combined in a fixed ratio. Okay, and what we tend to encounter in our everyday life is that we actually don't encounter individual elements. We actually encounter and we use, we're exposed to compounds. We're actually exposed to, and we use compounds rather than elements. Okay, so we encounter compounds or more compounds than elements, than individual elements in our everyday lives. So it would make sense then that this is what we want to study as we start building complexity with our chemical substances or substances in general. So we're going to take a look at several characteristics of both ionic and covalent compounds as we go through this section. We're going to talk about how they come together, how they form, and then very importantly, we're going to see how we name both ionic and covalent compounds, and we'll see the differences between the naming, or the nomenclature is a technical name for that. And then we'll do some calculations as well to show you how we can actually determine the chemical formulas for our different types of compounds. So as a reminder again, a compound is an example, one of the examples of the two types of pure substances, one being elements. Compounds is the other one, and we have two or more elements then that are combined in a specific ratio, and then these are held together by chemical bonds, right? We'll see the two types of chemical bonds in this section. As a good example and a good contrast between ionic and covalent, here we have an example of a covalent compound, which is water. So this is whatever this is, or Henry's spring water. So water, as you probably know, has the chemical formula H2O, H subscript 2, and then O. And then salt, in this case, if it's just pure salt and not, fortified with iodine or anything like that, this would be regular old table salt, just to specify the type of salt, because there can be many, many different types of salts, as we'll see down the road. Table salt here is sodium chloride, and sodium chloride has the chemical formula NaCl, Na for the sodium, Cl for the chloride. Now, at this point, we think, well, what's the difference between them? Are they similar in terms of how the components, how the atoms are bonded, how the elements are bonded together, or are they different? And the answer to that is they are very different, and we will see some of these differences in the next or in this section. So when it comes to anything related to chemical changes, chemical reactions, or when it comes to anything involving bonding, which is what this whole chapter is about, we are going to focus in on the electrons. Okay, so our electrons, we spend a whole week or two talking about subatomic particles, talking about electrons specifically, where electrons can be found, how we configure electrons, how we use a periodic table to determine that. There's a reason why we spent all that time talking about electrons, is because our electrons are the most important subatomic particles. Okay, and the reason why is because these are going to dictate chemical bonding. So how things come together to make bigger and more complex things. And they're also going to dictate chemical reactions or chemical changes. So I'm going to say reactions. I'm going to abbreviate that as RXN. That's reactions. So you'll see this throughout the remainder of our course. That's my abbreviation. You'll also see that in other places. So chemical reactions and changes. Okay, so this is why now the electrons are going to be the most important. If you think about your general idea of an atom, okay, at the center of the atom, you have your nucleus, and then outside of the nucleus, you have your electrons. You can think of, according to the Bohr model, they're orbiting around. So if I have one atom here, I have another one coming close by, just intuitively, you may think, well, if I want these two things to interact with each other, guess which subatomic particles are going to interact first? It's going to be the electrons, right? So that's why they're important. And the second point to that is not all of the electrons are going to be important. Instead, it's the valence electrons that are going to be most important. Okay, so again, in the last section, we talked about electron configurations, how we can determine the number of valence electrons. And this is the reason why now, because those valence electrons, which, if you recall, are the outermost electrons, or we can think of the electrons in the highest energy level, are the ones that will, in fact, dictate chemical bonding. So when it comes to bonding and reactions, electrons are the most important, not all the electrons, the valence ones. So we can focus in on the valence electrons, and we can actually use them in conjunction with other characteristics from the elements we can derive from the periodic table, and we can use that information to predict how the different elements are going to bond with each other, how they're going to react with each other. We can do all sorts of predictions just based on valence electrons. So the way that we represent our valence electrons is we use a system called the Lewis dot symbol. This is named after a scientist, Lewis. There are other things named after him as well, as we'll see down the road. But for right now, we're going to talk about the Lewis dot symbol. And what this is we have the symbol for the element, so the elemental symbol, and then we are going to represent just the valence electrons now as dots. Okay, so it's called the Lewis dot, or sometimes you'll see this being referred to as the electron dot symbol. Okay, they're used interchangeably. So, for example, if we have boron, we can write out the electron configuration for boron. So we have 1s2, 2s2, 2p1. The valence electrons are the outermost electrons, which belongs to the highest energy level, which is n equals 2 in this case. So we just add up those electrons. We have 2 plus 1. So that should give a total of 3 valence electrons. So we would have our B, and we put our valence electron as dots around that symbol. So I have 3 valence electrons. I can put my first one. It doesn't matter where you put the first one. I can start at the top, bottom, left, or right. I'll just start at the top. And then you go either clockwise, counterclockwise. It really doesn't matter where you put the second one, as long as you don't pair it up immediately. So you don't want to put that second one there. You want to put the second one on its own somewhere else. So I can put the second one maybe here, put it on the bottom or on the left. And the third one I put somewhere else as well. So like there, for example, I could have put it to the left. Any of those would have been combinations or reasonable Lewis structures or Lewis dot symbols for boron. Okay. As a quick reminder, when it comes to our Lewis dot symbols, and specifically now the valence electrons, we can use our periodic table to help us figure out our valence electrons for the main group elements. Okay, we can write out electron configurations, or we can just use the periodic table to help us get to the endpoint a lot quicker and a lot more efficiently. So the general trend here is the group number okay, and this is the A number that we're looking at, is equal to the number of valence electrons. Okay, I'll abbreviate valence electrons as VALE. Electrons. So for example, we just looked at boron. Boron is here. Boron is in group 3A. So boron has got 3 valence electrons. Guess what? Aluminum, also in group 3A, also has 3 valence electrons. Okay, if I look at something like F, which is fluorine. Okay, fluorine is in group 7A. Okay, so that means it's got 7 valence electrons. Okay, there's F. It's in 7A. So when I write the valence electrons, the Lewis dot symbol for fluorine, F, I have 1, 2, 3, 4. Okay, so I put 4 of the electrons in by themselves. When I have more than 4, and then I start pairing up. And you can start pairing up wherever you want. I can start here on the left side. So this is 5, this is 6, and then that's 7. Okay, so I have 1 unpaired electron in my Lewis dot symbol for fluorine. So we can use the periodic table to help us figure out the valence electrons. Remember now, that's your general rule. There are always going to be exceptions. One important exception to this is helium. Okay, helium is in group 8, obviously. It's a noble gas. But helium can actually only accommodate 2 electrons. So it only has 2, not 8. Okay, so we'll say helium is an exception to this rule or this trend that we're using. All right, but generally, we can use the location of the element on the periodic table to determine the number of valence electrons, and that's what we represent in our Lewis dot symbols for the elements. So when it comes to other trends in the periodic table, what we are going to see is that for our main group metals, so for example, if I have something like sodium, right? Sodium is in group 1A. So it's got 1 valence electron. Okay, there it is. That 1 valence electron, sorry, is the number of electrons, or is the electron that will want to be lost by that metal. Okay, so metals, the main group metals, for example, the dots that you see, those are the dots that they want to lose. Those are the electrons that they want to lose. For our non-metals in the second period, okay, so that would include non-metals now on the right side of the table. Second period would be over here, for instance. Okay, the number of unpaired dots is the number of bonds that the atom can form when they share electrons. Okay, so for example, in oxygen, it has 2 unpaired electrons, right? Out of the 6, remember now, oxygen is in group 6A. So it's got 6 valence electrons. We put them in according to what we talked about before. We end up with 2 unpaired electrons. So 2 unpaired electrons means then, guess what? It wants to form 2 bonds. It prefers to form 2 bonds. Okay, if we look at the example that we did up here with fluorine, okay, fluorine, as we saw in group 7, 7 valence electrons, 1 unpaired electron, guess what? It wants to form 1 bond. Okay, and remember now, this is just when it's sharing electrons, because we'll see different types of ways that it can bond to things. That's a shortcut, okay, to help us determine the number of bonds, as we'll see down the road. So not only do we use, or can we use, the Lewis dot symbol to represent the valence electrons for our elements, for our atoms, in other words, our neutral things. We can also use the Lewis dot symbols to represent ions. Okay, so ions are things that have charges. So we say ions, we can generally say are charged. So either positive or negative species. And species here again just means some sort of chemical particle, whether it's a small thing or a big thing. That's what the term species here represents in chemistry. So we can use our Lewis dot symbols to represent ions as well. We would need to take into account now what has to happen for those ions to form. So for instance, if we take a look at sodium, okay, we know that sodium is in group 1A, so it's got that one valence electron that we show here. We can confirm that with our electron configuration for the sodium atom. There's our one valence electron in the outermost energy level, the N equals 3 shell, the N equals 3 energy level. That's the one valence electron that we have here. Okay, it wants to lose that one electron, as we just said above. So if it loses that one electron, we end up with a new electron configuration now that looks like this. So we've lost the 3s1 electron. What we end up with is a species that has now a positive charge. So that electron is now gone. Okay, this electron is lost. I'll put lost in quotations. We don't just lose track of it. It has to go somewhere. Where it goes right now is irrelevant. We'll talk about it in a second. But it goes somewhere else. So it's not with the sodium anymore. So because now the sodium that we start with, remember, it starts off with 11 protons and 11 electrons. When it loses that one electron, now it's got 10 electrons, but we still have the 11 protons, right? We don't mess with protons. So let's just say this right now. We don't mess with the number of protons. That stays the same. If we change the number of protons, we change what that element is, and we can't do that in normal chemical reactions. So now we have an excess of one positive charge. If we just look at charges. And this is what we write now as our charge on the sodium, and that's the sodium ion. That's our Lewis dot symbol also. Remember, the Lewis dot symbol shows a valence electron. We've lost that one valence electron, so it's gone. It's replaced now by the positive superscript. Okay, we don't show our core electrons in our Lewis dot symbol. In the case of oxygen, right, oxygen is in group 6, so it's got 2, 4, 6 valence electrons, right? Oxygen has it has atomic number 8, so it's got 8 protons. The oxygen atom, 8 protons and 8 electrons. Excuse me. So overall, the oxygen atom doesn't have a charge. Now, what the oxygen can do, right, with those 6, it actually wants to gain 2 more electrons. And by doing so now, we end up still having our 8 protons. That doesn't change. Now it gains 2 more electrons. So now 8 plus 2 gives me 10 electrons. If I look at my charges, now I have an excess of 2 negative charges. So what I write then is I show that my oxygen starts off with 1, 2, 3, 4, 5, 6. It has now gained 2 electrons. So I put those electrons in. And you'll notice now the oxygen is going to have 8 electrons around it. This has a charge on it of 2 minus or minus 2. If you have a Lewis dot symbol with a charge, you have to put that in square brackets like so. Okay, that's the notation that we use. I know this doesn't look like square brackets here, but that's what they're supposed to be. Okay, that's the notation for writing the Lewis dot symbol for these elements. I'm sorry, these ions, and specifically now this negative ion, this anion that has a charge on it. All right, let's take a look at another example, and let's do the fluoride ion, F minus. Okay, we'll kind of walk through this. So we've used fluorine already. So fluorine, the fluorine atom has 7 valence electrons. Okay, so we have F, 1, 2, 3, 4, 5, 6, 7. Okay, so our fluorine atom, let's see, how many protons do we have in fluorine to begin with? Well, we have 9. So we got 9 protons. And we have 9 total electrons. So that's your 1s2, 2s2, 2p6. I'm sorry, 2p5. Okay, so those are your 7 valence electrons, but it's got a total of 9 electrons, right? And we in our Lewis structure, we just show the valence electrons, which are the 7. So 9 protons, 9 electrons, so overall neutral, no charge. What we're saying now is that we end up forming F minus. So F minus means that we've actually gained 1 electron. Okay, so now instead of having 9 electrons, now we have 10 electrons. I still have my 9 protons because I don't mess with my protons. So that gives me a total charge of -1. Okay. Now, if I've gained 1 electron, guess what? I have my 7 that I started with. 1, 2, 3, 4, 5, 6, 7. Now I'm going to stick that other electron, extra electron in right here. I'm going to encompass this in square brackets, and then the charge goes as a superscript on the outside. And that is your Lewis dot symbol for the fluoride ion in this case, right? This is not fluorine anymore. This is something different. F with a minus charge is called a fluoride ion. That's the name for that ion. And we'll get to the naming down the road.